Hi everyone, hope you're having an amazing day. Today we're going to talk about buffers. So buffers are solutions that resist changes to pH when an acid or a base is added. And so, for example, water is not a buffer. If I take some water, which starts at pH of 7, let's say, and I add a few drops of HCl, the pH is going to drop dramatically and maybe go to a pH of 2 or a pH of 1 even. So it drops from 7 to 1 or 2. If I take that same water that starts at 7 and I add a few drops of, let's say, sodium hydroxide, which is a strong base, the pH will jump up maybe to like 13 or 14. And so that would not be a buffer because it does not resist changes in pH. That means the pH changes dramatically when you add an acid or a base. A buffer, though, is a solution that if I add a little bit of acid or base to it, the pH of that solution is not going to change. And the buffer does not have to hold the pH steady at 7. It just has to hold it steady, but at any pH. So some buffers are acidic, so they'll hold, let's say, the pH at 5, and no matter how much you add to it, it's going to stay at 5. Others are basic, so they'll hold the pH, let's say, at 9, for example. So each buffer has a different pH, but it keeps that pH steady. In our body, we have a lot of different buffer systems so that our blood remains at a certain pH level so it doesn't go up or go down, because that would not be good for our organs, for example. So how do you make a buffer? A buffer is actually a solution that's made up of two different components. It has to be a weak acid with its conjugate base, or a weak base with its conjugate acid. So like I said before, a buffer doesn't have to hold the pH at 7. So if I have a weak acid with its conjugate, then again, maybe that weak acid with its conjugate has a pH of 4, for example. So then it would hold the pH at 4. Or it could be a weak base and its conjugate. So that would be my example that I said would hold a pH at 9, for example. So an example of a buffer that is a weak acid with its conjugate, maybe I can have some hydrofluoric acid, HF, which is a weak acid. And if I take that and add some sodium fluoride so that it has a fluoride ion in it, then that is a weak acid, and this is its conjugate base, right? This was meant to be a capital F. I just can't write very well on the iPad here. An example of a weak base with its conjugate, maybe I have some ammonia, NH3. That is a weak base. And its conjugate, maybe I have some NH4Cl, which is a source of NH4+. And so that is a weak base, and this is its conjugate acid. So if I take those two, mix them together with water, or if I take those two, mix them together with water, that would make a buffer. So a buffer is made up of two components, an acidic component and a basic component. Here would be, this is the acidic component, and this is the basic component. So they are an acid base conjugate pair, and so they only differ in that one of them has an extra H+. So between those two, this has an extra H+. Between those two, this has an extra H+. So what happens is if I take my buffer and I add some hydroxide ions to it, what will happen is, because this is basic, it's going to react with the acidic portion of the base. So if I take some hydroxides and add it to this buffer system, it's going to react with the HF. If I add it to this buffer system, it's going to react with the NH4+. If instead of adding hydroxides, what if I add some H+'s to the buffer? Then it reacts with the basic portion, because this is an acid, so it's going to react with the base. So if I add some extra H+'s to this system, this buffer, then it's going to react with the F-. If I add it to this buffer, then it's going to react with the NH3. So let's take a look at what happens when you add some extra H+'s or some extra OH- to a buffer system. So let's start with the NAF and HF system. So again, this is the same thing as saying I have HF and then from the NaF, the F minus is what I care about. The sodium ion is just a spectator here. So this would be our acidic portion. Oops. Right here. This is our acidic portion. And then the F minus would be our basic portion. So let's say I take some H pluses and I add them to this buffer. Which of these two, the HF or the F minus, is going to react with my H plus? Well, since this is an acid, then the base is going to react with it. So what's going to happen is I'm going to add it to the F minus. And what will I form? I will form some HF. Now, if I do this and I add only a little bit of H pluses, well, what's going to if this was my limiting reactant, basically, I only have a little bit of this, then what's going to happen is I'm going to use all of the H pluses, the extra H pluses, I'm going to use them all up. And I'm going to use a little bit of the F minus, but I'll have more of it left because it's not my limiting reactant, it's the one in excess. So I'm going to use some of this up, but not all of it, and I'm going to produce some of this. So what you'll have left is you don't have any more of this because it's used up, and you just have still F minus and HF, which was your original buffer. Just different concentrations maybe, but you still have both components of your buffer and nothing else, and so the pH remains about the same. Now let's try it if I were to add a base to it. So let's say I add some hydroxide ions. Well, now which part of the buffer would react with it? So since this is a base, I'm going to react it with the acidic portion of the buffer. And so I would react it with my HF. And so what I'll form would be H2O and F minus. So again, if my hydroxide was my limiting reactant, so I add just a little bit of the hydroxide ions, then that's going to get used up, so I don't have any of this anymore. I'd use some of my HF up a little bit, but I'd have some left over if it's in excess. And so what I have left at the end after this reaction happens is some of the HF, some of the F minus, which are both part of my original buffer, and some water, which does not really affect the pH. And so my pH remains about the same. Let's look at an example where I have a basic buffer. So my example up here, this was an acidic buffer, so this would hold the pH at lower than 7. This is a basic buffer that would hold the pH at higher than 7. So ammonia is a weak base. This is its conjugate acid, and really from the NH4Cl, it's NH4 plus, really, that is my conjugate base, right? So this is my, conjugate acid. So there's my base, and this is my conjugate acid. So let's say, just like the previous example, I had some H pluses. Which part of the buffer would react with that? Well, H plus is an acid, so the base would react with it. And so the NH3 would react with it. And you'd form some NH4 plus. And so at the end of the reaction, if my H pluses were my limiting reactant, then that gets used up. Some of this gets used up, some is left remaining, and I form some extra NH4 plus. So I'm left with these two, which are my original buffer, so that does not change my pH very much. Now let's look at if I add a hydroxide ion to that. So which portion of the buffer would react? This is a base, so the conjugate acid would react, and so I would react it with the NH4 plus. When those two react together, I form water.
And it's like green.
And NH3. And so again, if my hydroxides were my limiting reactant, that gets used up. And I use up some of the NH4 plus, but not all of it, so some of it remain, along with the NH3, so that's my buffer system. And I have some extra water that doesn't really affect the pH. Now, each buffer has a buffering capacity. Remember, in all of these I said, if the amount of H pluses or OH minus I'm adding is small, is my limiting reactant. If I add too much of the hydroxides, for example, in this case, where now this becomes my limiting reactant, then this is used up, and I have extra hydroxides. In that case, my pH will change. So each buffer has a buffering capacity. It can only handle a little bit of H pluses and OH minuses added, after which if I add too much, my pH will change and it will no longer be a buffer system. Hope this helps, and I hope you have an awesome day.